All right, here we are. This is ELE 111 RCRL series circuits. Fifth problem. This is 5B. We're actually going to get in and solve the circuit that you see at the top. Is the problem that you were looking at in file 5A of the same title. That is the circuit. We're going to actually solve to IR1 and IC1, it's the same current because it's a series current. I also noticed that the current will split here, not evenly. Most of it will go to the capacitor because it's a smaller value. What I also know about this drawing is that the parallel chamber, which is located over here, is going to have the same, you got it, which is located right there in the blue circle. We know everything about what's in the blue circle. Welcome ELE 111 to sections 16.6 and 17.6 series parallel RL and RC circuits. What we have before you today, and the first step that I did was I took all the parts and I redrew them as a box and labeled them impedance Z1, Z2, Z3, and Z4, as you can see right here in the red circles. And I recommend you try to solve your circuits like this yourself. I recommend you redraw lots of pictures. I recommend you use a lot of paper and you write everything down. This can be very confusing. Now, first thing I want you to notice is a parallel combination, which we've already discussed. But right over here is a little sweet spot of a series circuit. And that's what I'm going to attack right off the bat here. I'm going to attack this series circuit because I can. Now, I don't have to. I can start this circuit right here if I want and compress that, and boom, you're automatically into a series circuit at that point with Z1 and Z2. Wouldn't that be great? So I combined Z1 and Z2 by simply grabbing the impedances. This is starting to get a little easier, I hope. I grabbed the impedances, added them together, and this is what I get. I get Z1 plus Z2 is equal to Z1, 2. You might want to add that to your notes. Okay, so this circuit is toast up till now. We can go to the next circuit, and you see I have transferred my information over so that I have it on the next picture of the circuit, showing that I've compressed it and reminding me exactly what that value was that I solved for. Next step, I take a look at the circuit. I start on the outside going in, and I see a parallel combination, and I run through product over sum. Did I have to? No, I could have used this. Maybe a good exercise would be to use this, because you're going to have to learn how to put brackets around everything. And this formula should produce that answer. Go ahead and give it a try if you like. Pause the video, but keep making good notes. That's going to be your secret. You're not going to remember any of this if you don't take notes. And you're supposed to be getting an online instructor here, which you are. But if you don't write anything down, you're losing the experience, okay? All right, next drawing. Wow, this circuit has now been slayed into a series circuit. This is what we live for, is to be able to combine everything together. And we've got two modules here of series circuits, and we just add them together right here to get this answer. Go ahead and try that. See if you can get it. Make sure that you see the series channel, and we'll move on to voltage slide. So here we are. We've broken this circuit down. We've crippled it into one impedance. You'll notice that I call it Z1234 so that I know that it took 4 boxes to compress it, but it's otherwise known as ZT. That's the only thing that circuit's good for. That's the only thing that circuit's good for. Now, in another lighter note, the observation that IT is... So, now that we know those two resistors are in series, the two up at the top, with the supply, we can just use this equation to calculate the total current in the circuit. And now we know everything about we know everything about IR1 and X sub C1 except their voltages. Here, let me look at something real quick. Okay. Here's the circuit redrawn. Here it is. Okay. And it's back to a series circuit. I've dropped in the two resistances that are sitting back forward. Okay, so here's where we actually calculate the total impedance by adding these two blocks up to get I total. And therefore, we know that this is true, right? Now, the only thing missing are the two voltages. Well, we've got the current and we've got the impedance for both of them. And that allows us to make that computation right here on the screen that you see. And slowly but surely, you're finding out that, hey, all I really need for any component is to find its voltage, then I can get its current, or I can find its current and then I can find its voltage. Because there's only three unknowns here, and if we have 2 of them already before us, we can calculate the voltage. Whereas if we don't, maybe we only have the voltage here and the resistance, and we need to find the current. Well, then we just pull out Ohm's law and we do the same thing. Okay? So, in summary, here's what we know so far. We know everything about resistor 1. We know everything about capacitor 1, which is bundled up inside this blue circle that I keep running up at the top, the tornado. All that information is bundled up there. Okay, next slide. Here's the information summarized again about what we know so far. And we note that, we would like to go get this voltage right here. It would be cool because there are 2 components, namely a resistor 2 and a capacitor 2 that are sitting out there like this. And there's the resistor, there's the cap. Man, if we could find the voltage, of that impedance module Z34, okay, then we'd be home free. So I did you a favor here and I said, hey, I know there's 10 volts. Right here. And I just finished calculating the fact that I know what the voltage of the 2 parts are located in this little circle up here. Here it is. It's 7.143 at an angle of 63.435. That's the voltage of resistor 1 and capacitor 1. And if I take that away from 10 volts, look what you get. You get a voltage that equals the 2 parts that are up here in parallel. How did you like that slick move? That's called using Kirchhoff's voltage law to back out the remaining voltage when you know everything about your circuit except one thing. So to re-summarize that again, what I'm going to say is we know this voltage. We know this voltage. It's right here in yellow. It's a combination of the capacitor and the resistor voltages that we found out on the last page. Actually, I've got those reversed. So let me fix those. Well, let me fix those. VC and VR. Okay? Kirchhoff says that the total in the battery, subtracting everything else in the loop, leaves me with VZ34. And that's cool. That's my answer. Now, you say, wow, there must be another way around this. Yeah, there is. There is. How about Ohm's law? How about using Ohm's law? Option number 2 says V equals I, Z, and the I going in is in red up here at the top. You see, the I is the I total, which we solved back here a long time ago. So we grab that I total and we grab the impedance that we see right here and we drop it down and we run a calculation, a multiplication, and we find out that the two answers match. Wow, does that surprise you? That doesn't surprise me. You may have to stop this video to make notes and write things down because of the speed with which it's moving. But here we go. We have just computed the same thing twice. And then you're going to say, hey, could there possibly be another way to do this? And the answer is yes. And the reason the answer is yes is this is a series circuit on this page. And so this voltage, which is 10 volts peak to peak at angle 0, times that impedance divided by ZT, here it is, will compute exactly the same value. So what you're seeing is this is not only challenging because it's series parallel, it's challenging because you don't want to write anything down. You don't want to consider more than one option. You have to be remaining flexible. You have to look at a circuit and go, hey, that's series. I can use voltage divider if I do it right. I can use current divider if I use it right. I can use Ohm's law if I use it right. So we've found quite a bit of information. I'll tell you the only thing that's missing in this section right here in black up top, we have to find the current of resistor 2 and the current of capacitor 2 as well. We have current of capacitor, done that yet. So here's our circuit, and you see we've already got the voltage here for all of these. Well, that's all we need for current. We need voltage and reactance, and we need voltage and reactance. And that allows us to break the voltages down real quick right there before you using Ohm's law. Could I have used current divider here? Oh, yeah. Oh, yeah. We do have the current up here in yellow. We do have this current. We could use just this circuit and the ZT from that circuit and prove to yourself, if you have the time, that you can get these same two answers using current divider. All right? What else do I want to say? There was something else I was thinking about, and now I can't remember. Okay, So the question is, here's this series parallel circuit. You see it with all four parts sitting before you. Who dominates? I have no clue if I'm looking up there. I have no clue. I have to look to the impedance total of the circuit. Being that it's minus 63, which means it's closer to negative 90, the capacitor is dominating the circuit. Does that make sense? Okay, last couple of slides. We want to draw phasor diagrams, and realistically, I don't have to say a whole lot here. It's pretty obvious if you look at it that we have all the voltages here and we have all the currents here. If you have those and you have a clue that there is 90 degrees in each of these quadrants here, and there's 90 degrees on the bottom of each quadrant, then you shouldn't have that much trouble drawing these phasor diagrams. After all, I'm not asking you to use graph paper. I'm not asking you to be exact. I'm asking you to approximately draw the phasor diagrams in relation to their proportionality. For example, the power supply to this circuit is this long. If I'm going to draw the phasor for VR1, for example, which is 3.19 volts right here, I'm not going to draw it this big. It's out of proportion. You've got to be reasonable. You've got to take and scale back that 3.19, and then 2.85 is going to have to be even smaller than 3.194. But the important part is to incorporate the proper phase angles into all of your drawings. So I've taken the time in many of these problems to continue to ask you, who dominates the circuit? You can tell by looking at the phase angle, in polar or in rectangular. Draw a phasor diagram for voltages, for currents, and I keep drawing pictures for you because I know where your weaknesses will be. I know what you will not pay attention to and what you will drop by the wayside. And these phasor diagrams are a pretty important part of the class and pretty important part of your homework assignments. So, if you've solved the circuit completely, you should be able to do these two phasor diagrams. Okay. Last but not least, voltage and current checks. I don't expect you to do this with all your problems. You've got answer keys. You look in the back of the book, you check your answer key, your answer is close, you're good. But let's say you're on a deserted island and all you've got is your iPad and a circuit like this and a TI-89, and you need to know if the circuit's right. Well, then, if that's the case, you need to be able to put the voltages back on the grid here. I'm in need of figuring out why the colors have gotten so light, but they have. You need to be able to figure out if these voltages here pan out. Well, you can do a Kirchhoff's voltage law check. It would involve adding the voltage of R1, the capacitor 1, and one of these two components. They share the same voltage, so they're in parallel. And as you can see, it checks out, which means I solved the circuit right. And if I come and grab for the currents, if I come back and grab for the currents, we figure out real quick that we know what the current is up here. It's IT, and then it splits. Well, it makes sense that those three currents should add up to I total right here. And if you add them up, these two currents, they check. And you've successfully finished this problem. Congratulations.